All right, recording's re-rolling. We're near the end of class now. I'm gonna go around and ask everybody to give me their prediction, and then we'll roll it, see how this works, and then I'll solve it with you guys. All right, so Elijah and friends, what'd you guys get? Oh, sorry, you said 0.572. Oh, I'm so sorry. Yeah, you're right. Ooh, that was more. All right, oh, good. All right, Scarlett and friends. 5 2 meters. All right. All right. How about Iska and friends? 2.722. Okay. 2.722 meters. Okay. Oh, Nicholas and friends.
0.205.
0. What?
205.
205. All right. Studi and friends. Rick and friends. All right. Connor and friends.
0.3.
And Layla and friends. All right. All right. So we're gonna roll this ball. Well, I'm gonna roll it down, release it from rest, and we're gonna find out the answer. Somebody's about to win some peanut butter cups, and then I'll go over the solution with you guys. Okay, there we go. So it's right down here. Truth be told, I don't know the answer myself, but we're gonna find out. We're gonna find out. All right, 200 centimeters right there. All right, we're just gonna do one trial. Now, you guys know, realistically, actually, what do you guys want to do? Do you guys want to do one, or three, take an average? Three and an average? Three and an average? Okay, that's what we'll do. We'll do three and an average. How about that? That's good practice, right? Here we go. Trial one. I'm getting 63 centimeters. All right, so just keep track of this. 63. All right. Trial two. Getting 64 centimeters. All right, and trial three. Ooh, 66 centimeters. All right, divide that by 3. 64.3 centimeters. All right. So the answer was 64.3 centimeters, or 0.643 meters. All right, so who got closest to that? Is it okay, this is, I think it's Elijah. Let me double check. All right, so 643 minus 572. All right, so this is off by 7 centimeters. Right here, 64.3 minus 57.2. Okay, this is off by 7.1. That's 7.5 minus 64.3. It's off by 13. I think Elijah's team's closest. Is that correct? All right, you guys get what I'm getting? All right. Peanut butter cups. Elijah and friends. All right, you guys ready for these? Whoa, good job, guys. All right. All right. You guys have fun with that? You guys like that? All right. So here, let's go over the answer. All right. So here, guys, take out your notes, or keep writing on the paper you're writing on. All right, here we go. All right. So I told you guys it's two parts, right? The first part is we have to consider this part where it's like rolling down the incline. That's going to be, here, go step by step. Conservation of energy. Okay? Oh, guys, what kind of energy at the very top? All potential energy. That's for MGH. MGH right here. Now, guys, by the time you get to the bottom here, guys, everybody look here. Think about this. Where's the energy go? Into what and what?
Kinetic and rotational.
Boom. Linear kinetic and rotational kinetic. Sometimes called translational kinetic and rotational kinetic. That's that, right? Right? Okay. Now, this I is related to this M, and this omega is related to this V, right? That's where I throw you guys this hint. You guys are probably playing off this, right? Like 2/3 mr squared, right? Because it's approximately a hollow sphere would be the this model there. Okay. So in place of I put 2/3 mr squared. Okay. Now you guys remember omega is v divided by r. Okay, you guys remember that? Oh, so v is meters per second. Omega is radians per second. So you have to divide by r. Okay. Now it's being squared, so I went ahead and just squared it. You see that? Okay. Do you guys see what's going to cancel out? The r's. Boom, boom. R's cancel. You guys see that? Right. So I end up with 1/2 mv squared plus 1/3 mv squared. Common denominator is 6. It ends up being 5/6. Right? You see like that? Right. Oh, guys, what cancels out also? The mass of the racquetball. You could have plugged it in. Shouldn't lead you astray because it just cancels out anyway. Right? And what are we really solving for here? What are we solving for again? V. Good. V. Right. So you do that, you get 6/5 GH. Oh, here. Let's get a number. What's somebody tell me what height did they get for this was H1, right? Or that's H1. What'd somebody get for H1? 0.95. Right. So square root of 6/5. Do you guys want to use 9.8 or 10 for a G? Okay, 9.8 meters per second squared. Right. You said 0.95. No, yeah. Well, how did we go to it? That is a lot for each one. What do you guys get? 0.27? That sounds closer. Yeah, 0.27. Oh yeah, okay. I think you're looking at the wrong age. Yeah, 0.27. That'd be meters right there. Yeah, because we're talking about just that incline raised up, right? Not H2. H2 was like the whole like lab table. Right, so H1. Right. So throw this on here. I'm getting square root of 6/5 times 9.8 times 0.27. 0.27, right? And that is that right? Did you guys get something close to 1.78 meters per second? Did you guys get something close to that? Pretty close. Maybe not exactly, pretty close. Guys got? Okay. Oh, want to show you guys this too. I know yesterday it was near the end of class, but you guys remember this right here? Remember this? That's how fast the ball rolling. Right now, you could have used forces and dynamics to solve it. You would have gotten that. Although it's kind of tricky to do this. That they're going to emphasize that so much. But conservation of energy, I think you should be able to do this. Although it's a little tricky. That's what we just did, right? So this answer has been here on a poster for a long time, right? Right? Is that okay? What is the speed of anything if you release it from rest? It's usually some version of square root something GH. Like Galileo drops the ball, how fast it lands, square root 2 GH. Right? This is gonna be slower than that. Oh, 6/5 GH. Square root of that. All right, so we did. Now we're on to part 2. So we know the speed. Now this is speed at some weird angle, right? Okay. So the second part is this projectile, right? What do you guys get for the angle? What'd you get? 7 degrees? Did you guys get something pretty close to that, about 7 degrees? Right. Now maybe everybody's got slightly different measurements. Maybe you didn't get exactly that. Right. Here, you could have either measured it or you could have done here. Let's do it from an inverse sine. Right. Because if this was 0.7 centimeters, you guys said, what's inverse sine? These two would have a sine relationship with this angle, right? What's inverse sine of 27 centimeters over 200 centimeters? Let's see. Oh, 7.75 something degrees. Right? Maybe I'll call it 7.8 degrees. Is that okay? 7.8 degrees. You guys are saying 7. I'm getting 7.8 by the calculation. Let's do 7.8 degrees. Right? So if you do that, right, let's take this 1.78 meters per second multiplied by cosine of 7.8 degrees. Okay, 1.78 cosine 7.8. And that is 1.76 meters per second. That's going strictly across the room. Okay? And then if I put in the sine component, put in sine here, this ends up being 0.24 meters per second. And that's strictly downward, isn't it? Right? So it's kind of like you chuck it downward that fast. Think about vertical. Right? Now, if you plug in the vertical constraint, right, it would look like this. Here's the height to that it falls. Right? That's where you run into quadratic formula. That's where I throw you guys that hint. So you get how much time that it should be in the air. What'd you guys get for the time? Elijah, what'd you get?
0.349 seconds.
0.349 seconds. Right. I know we're running up against the bell, so I'm kind of skipping stuff a little bit here, but you guys see like the process where that come from, right? I know that this is a challenging problem. Right. And then finally, horizontal motion. So if you take the 1.76 meters per second going across, 1.76 meters per second going across, right? Across the room. And you multiply it by the time of fall, right? Which it's shorter than if you just dropped. If you just dropped it, it should take a little bit longer than this. If you're kind of chucking it down a little bit. Okay, then we got 0.349 seconds. That's what Elijah got. Okay. So let's put it all together, see what the distance should have been. 1.76 meters per second times 0.349 seconds. That comes out to 0.614 meters, about 61 centimeters. Oh, where? Oh, and look at there, look at there. The actual value ended up being 64 centimeters, and the closest guess was like 57 centimeters. Yeah. All right, so nice job, guys. Nice job. All right. AP class tomorrow. You guys think you can do AP class by tomorrow? All right. And you guys have a great rest of your day.